Hello again, this is Math 2231 remote delivery for April 14th, 2020. This is part 1, and I encourage you to test your understanding as you go through by hitting buttons like this. My favorite teacher in high school made us memorize the poem If by Rudyard Kipling. I'm not going to recite the whole one, but I think of it often. If you can force your heart and nerve and sinew to serve your turn long after they are gone, and so hold on when there is nothing in you except the will which says to them, hold on. The poem has a later line like this: yours is the earth and everything in it. So these are not easy times, but if we're able to work hard enough, if our circumstances allow, teaching and learning can continue unabated. Grades will be earned and rendered, and your educational goals need not be deferred. I encourage you to do this, to engage and persevere. That's what champions would do. Okay, last time I promised you whenever we ended up with an expression for the area under a curve to be the summation, I promised I would review summations. That's the purpose of part 1 here. So if I have two integers, n and m, and n is less than m, then I can talk about having the first number and the next number and next number and so on and so forth. This is just a sequence of numbers indexed by those integers beginning at n and ending at m. But if we want to add them up, so we just add them all up from first to last, that ends up being a number. For large lists, this could be cumbersome notation, so that's the summation notation, and this expression that we just talked about is represented by this compact form. The summation, that's what the sigma means, as I goes from 1 to n of a sub I. So we let I equal n, we get this term, and then we move further and we say I equal n plus 1, we get this term. We go all the way up to m. That's what this notation means. The I is called the index of a summation. It is a dummy variable, and that's what the notation tells us to do. Add up all the a sub i's for all integers starting at n and ending at m. Here's some examples. If I equals 0, we get this. If I equal 1, we get this. If I equal 2, we get this. Dot, 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 all the way. If I equal 4, we get this. And that's what it adds up to. Here, what happens is we put I to be 4, I to be 5, and I to be 6. And when we simplify that, we get this expression. And here we go from 1 to 4, and this is what we get. There are properties of summation that we're going to be using in some calculations that we do. One thing is we can factor constants out of a sum because we have a constant times each a sub I. And so that means, using the distributive property, we can jerk this constant through the summation sign. Again, that's the distributive property. And likewise, since addition is commutative, we can break a sum across to sum or difference. And in fact, I'm going to say this a different way. This means we can do summations term by term. And this does rely on the fact that addition is commutative. There are some things that are not true and mistakes students often make. The summation of the product is not the product of the summations. There are all kinds of middle terms. Likewise, the summation of the quotient is not the quotient of the summations. Not even close there. Some additional properties. If I sum from I equal 1 to n, looks like the n was cut off here, it's just the constant pulled out times 1, 1, 1, and so on and so forth. So you get c added to itself n times. Said another way, when I equal 1, you get c. When I equal 2, you get c. When I equal 3, you get c. So it is c times n. A lot of students make mistakes on this, so think about that rather deeply. If we sum the first n integers, that means 1 plus 2 plus 3 plus 4 plus so on up to n, we get n times n minus n plus 1 over 2. N times n plus 1 over 2. This formula, for example, if I was 4, it would be 1 plus 2 plus 3 plus 4 would be 4 times 5 over 2. And if you check the arithmetic, you'll find out that that is correct. Here, we will need the summation from I going 1 to n of I squared. Now this means this starts out as 1 plus 4 plus 9 plus 16 plus 25, so on up to n. It's going to be this expression. So if we go 1 plus 4 plus 9 plus 16, n would be 4. So it is 4 times 5 times 9 all over 6. And last but not least, we have this one. The summation from I equaling 1 to n of I cubed is equal to this expression. I find it really interesting from a number theory point of view that this summation is the second summation exactly squared. So this is equal to the summation of all this business squared. Anyway, again, it is the same thing. If I went and looked at what this would be, this would go 1 plus 8 plus 27 plus 81. I went up to I being 3, so that would be 3 times 4 over 2 whole squared. Alright, so here's an example for you to do. Please hit pause and test your understanding. Now, let's see how you did. Well, you start by having to expand this, so that's going to be 9 minus 12i plus 4i squared. And now we'll do this term by term, so I get this expression, and this expression. On these last two, I'm going to pull the constant out. There I have a constant of 12. Here I have a constant of 4. I can pull those out. I'm going to repeat this last step on the next slide. There it is, and now I can use my formulas. Here I'm using n times n plus 1 over 2, and here I'm using n times n plus 1 times 2n plus 1 all over 6, and that makes the calculation pretty quick. Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care of yourself and others, and I will see you in the next video.